Our next application of constrained least squares is linear quadratic control. Like portfolio optimization, this is a topic where there are multiple entire courses you could take on nothing but just this one topic. It's also something like portfolio optimization that's widely used. So let's look at what this is. The setting is we have a linear dynamical system. So we have a state, xt, that's our state here, and it's an n vector. We have an input, ut, and I'm using the traditional terms that people would use in control. That's an m vector. I have an output, that's yt here, related to the state. That's the output yt. At is called the dynamics matrix. B is called the input matrix. C is called the output matrix, as some other sensor matrix is another name for it. And here we have a linear dynamical system. Now, very often here, A, B, and C don't depend on T, in which case it's called a linear time invariant dynamical system, or an LTI system. And I should also mention that these usually don't represent xt, ut, yt. They don't represent the actual value of the quantities of interest. They're usually deviations of those quantities from some standard values, right? So it should be the deviation from some standard operating condition or something like that. And usually it's set up in such a way that x equals 0 is good. That means that the system is working like the way it's supposed to. This is just usually. U equals 0 means that the input is kind of what it would normally be or something like that. So that's the idea. Okay, so linear quadratic control, the basic idea is we are going to choose a sequence of inputs over some time horizon. The time horizon we're going to take is with the times t equals 1 going up to capital T. So we're going to go capital T steps into the future. That's going to be our time horizon. And our job is to choose a sequence of inputs that's ut for little t equals 1 to capital T. Actually, for the ut, we only have to go up to t minus 1 because xt only depends on ut minus 1. Okay. Now we're also going to go ahead and choose the state as well, the state sequence. So that'll be x1 up to x capital T. Okay, and so what we're going to do is we're going to have two objectives. It's a bi-objective problem. In fact, this can easily be, you can add more objectives, so it's a more than bi-objective, like a multi-objective problem. But the simplest objectives would be two things, and these sort of have names. The first one is this. It is the sum of the squares, essentially, of the outputs. And the idea is you want those small. In fact, in many cases, you actually choose the output to be literally the things that you want small. And that's, of course, equal to this. That's the same as this thing because C1, X1 is Y1. And so this is a measure. Some people call that a measure of regulation or something like that. It's you want the output to be small. And remember what the output is. Yt kind of represents a deviation from a desired state. So that's why you want it small. Small means everything's cool. And the input is going to be the sum of the norm squareds of the inputs. And remember, the inputs only go up to capital T minus 1 because that's the last input that matters to x sub capital T. Okay, so and then this has got another name. It's it's like the input energy or something like that, but it doesn't matter. That's it. So these are the two things, and you want both of them small. Now, so we put that together in a bi-objective. We scalarize those two objectives, and we write it as J output plus J input. Output means that the output is small. And input means that you're not using a big input to mess with this thing. And then rho is a parameter, it's positive, that tells you how much input deviation irritates you compared to output deviation. So that's all rho is. Okay. Now we also have here the dynamics, right? So that just tells you how the next state is related to the current state and the current input. And then we have two other constraints. And these are initial and final state constraints. The first one says that x1 x at little t equals 1 is x init. That's the initial state. And then x capital T is going to be the final state, and that has to be equal to something which is given, which is called x desired. X init is also given. So that's the idea. And there are many different sort of variations on this problem. In many cases, x init is the current state of a system, and x desired is 0. So it says, please get me from here to 0 over capital T steps. That's generally called the regulation problem. Another one is basically you're in some state, and there's a high-level command that says get to this state at that time, and then this would be non-zero, x desired. Okay. So here, in this optimization problem, we got a lot of variables, which is it's the state at all of the times, and it's the input up to, well, t minus 1. Okay, so this is the so-called linear quadratic control problem. It's to choose the sequence of u's and the sequence of x's. It's a big problem. Actually, what we're going to find out is it is absolutely nothing more than a constrained least squares problem. So, and it's a big one, but nevertheless, that is all it is. Okay. Oh, and I should add how it's used in control. Rho is chosen. I'd like to say there was some principled way to choose rho. There really isn't. What happens is you choose rho and you look at the trajectories, and if you like them, if the u is too big, then you crank. If u is too big, you crank up rho. If you'd like the output to be smaller, j output, you would crank down rho. So that's just the idea. And you kind of just look at it under simulation and have an idea of what you like. Okay, now let's see how this works. What we're going to do is this is you'll recall that this is y1 and that's up to yt here, and so we're going to minimize this big expression here. This is like this thing here is j1 j output, I think we called it, right? And this thing here is rho times j input, like that. Okay. And then we have the dynamics equations, and then we have the initial and final state constraints. Now, this whole thing, this big complicated problem here, it looks very, very complicated, can be written as just a constrained least squares problem, period. Just that. So we're going to write this big thing up here as minimize a tilde z minus b tilde subject to c tilde z equals d tilde. And I have to tell you what all those things are. So I'll start by telling you what z is. Z is all of our variables all stacked together. So it's the entire state sequence, and it's the entire control or input sequence. And so it's got capital Tn plus t minus 1 m variables. So it's a big thing. And if we wanted to extract, for example, the inputs from z, we would just slice into z and take the appropriate parts, and that would give us our sequence of inputs. Okay, so that's z. I still have to tell you what are a tilde, b tilde, c tilde, and d tilde. Okay. So let's first look at a tilde and b tilde. So a tilde is this giant matrix here. You have to put z here, and z, let's remember what z is. Z is x, the x's stacked on top of the u's. Now, a tilde is block, it's what people would call, it's block diagonal. Meaning, diagonal matrix, of course, is a matrix with, non-zero entries only on the diagonal. But here it's only these diagonal blocks which are non-zero. And so if I multiply this matrix by, x1, and this goes down to xt, and then u1, all the way down to ut minus 1. If I multiply this big matrix by this vector, and I do that blockwise, what I'm going to get is it's going to look like this. It's going to be c1 x1, and this goes down, c t xt, and then I'm going to get square root rho times u1, and then down to square root rho u capital T minus 1. Now, When you take the norm squared of this, well, how do you take the norm squared of a block vector? It's the sum of the squares of the norm squareds of the components. And you know what? It's norm squared C1 X1 up to, and then these are, when I square that, I get rho times norm squared U1. And you know what? That recovers exactly this, our objective. Okay? So that's how to write oh, and B tilde is 0. So there's no target. Actually, we could have B tilde non-zero. That means that you want your states or whatever to track a given trajectory. By the way, that also comes up in practice. But anyway, okay. Now we're also going to write these sets of linear equations as one gigantic set of equations, linear equations on Z. And let's see how we do that. Well, again, it's a big block matrix. The first one is A1 minus I, then zeros and all, and B1. And if I multiply that, if you multiply that in your head by this vector, right, which is the x1 down to xt, u1 down to ut minus 1, you'll figure out what happens. This first equation says the following. It says a1 x1 minus x2 plus b1 u1 equals 0. And that's the same equation as saying x2 is a1 x1 plus b1 u1. So that's the correct equation, the first one. And you can check that each of these rows give you the dynamics equations. This bottom one, I mean, it's very simple, but if you look at it, if you multiply this giant block row by this thing, it basically says x1 equals x init, and if you do it down here, you get x capital T, that's the final thing, is equal to x desired. That's your desired terminal state. So, okay, so all of this is just to say that we have taken a problem that looks pretty complicated, and frankly, it is kind of complicated. I mean, in classes, I mean, I teach classes on this, and it gets kind of complicated, and you're weeks into a class before you get to this and what the solution is. But the truth is, here we know. I mean, we just write it like that, and then it's solved. It's that we know you'd form a KKT system, and you'd solve it. By the way, the KKT system that you would form here would be extremely sparse. I'm sure it did not escape your notice that both A tilde and C tilde are extremely sparse. And so when we would form the KKT system here, it would be very, very sparse. And actually, it would be even more than sparse. It would end up being, it would have a very specific structure. And that means that, for example, sparse matrix method could actually solve it shockingly quickly. Okay. Okay. So what we've done is we've reduced the linear. This is the so-called linear quadratic control problem, and we've reduced it to a very big constrained least squares problem. That's it. And we just solve it. So we know everything about that. You just solve it. And then you're going to get, it means that the data in the problem are, I have to give you the AIs, BIs, CIs. I have to give you rho. That's a parameter. I have to give you X init and X desired. And that's it. And capital T, of course. And so from that, we will construct the optimal trajectory and input sequence for it. Okay. So we'll look at an example. It's a very simple one, but it gives you a rough idea of kind of what this does. I should say this is actually used very, very frequently. It's used in all sorts of stuff for control of cars, space vehicles, engines, all sorts of. It's just used everywhere. Well, things very closely related to this. Okay. So we're going to look at an example now. It's going to be a baby example just to give you a rough idea. So here's our matrix A. I don't know what this thing is. I mean, it's it doesn't matter what it is. Maybe it's a mechanical system. Actually, it doesn't matter. Here's B, and here's C. Again, not that any of this would mean anything to you, but it's a small example. Here's the initial condition, probably generated randomly, just to give you a rough. This just and then the final state that we're going to take you to is 0, and we're going to do that in 100 time steps. Okay. So that's what we're going to do. In 100 time steps, we're going to take you to 0. That's called, by the way, that's a special case when x desired is 0. The problem is called the regulator problem because we're regulating the state to 0 being some kind of desired state. Okay, so that's going to be our example. it's going to be pretty big. M, which is the dimension U, the input is 1. So we're going to calculate for ourselves 99 inputs, they're scalars. And we are going to calculate a state trajectory, which is 100 long, and each state has dimension 3. So again, if I did my arithmetic right, which there's no reason to believe I did, but if I did in my head, I get 399 variables. Honestly, that's just a tiny problem, right? But even so, it can be solved like with shocking speed, just because of the special structure. Okay. All right. So here what we've done is here we just simply vary rho, solve the problem, and calculate J input and J output. And sure enough, you get this beautiful trade-off curve. This is what you'd expect to see as a trade-off between these two objectives. And it says the usual thing. It says you can have J output low, but you're going to do that by it's going to cost you lots of input, right? And you can have J input low, and that's going to cost you too. In terms of J output, right? So, and we're going to look at 3 points on the trade-off curve. Rho equals 1, rho equals 0.2, rho equals 0.05. And let's think about what these mean. Rho scales how much we care about the input. So that's what rho does. And so if we look back here, let's think about it before we even look at the plots, what we think we're going to see. What we're going to see is as you reduce rho, what should happen is the input size should get bigger. I mean, that's what this means. That's also shown directly here, right? But also the output size should get smaller, right? And so, because that's really what the trade-off is. In some sense, you are spending a large input in order to achieve a small output. I mean, that's kind of what this is about. That's the trade-off. So we'll look at these 3 things, and we'll take a look at what the trajectories are. And what we're going to show you is the input applied. The input, it's on the same scale in these 3 things, right? So, and sure enough, look at this. When rho is 1, which increases, as we increase rho, we increase the amount we care about the input. And sure enough, look at that. If you compare this and this and this, you see U is roughly speaking getting smaller. At the same time, Y is kind of getting bigger. I mean, not dramatically so, but the point is if you kind of look in here, you'll see that, Y is, it's pretty small. Sorry, no. Sorry, that's not small. Small is 0 here. Yeah, so let's see. Yeah, so it's right that as Y, here, it gets bigger. Okay, so that's how that works. All right. Next topic. It's related, and it's actually a very common way that the linear quadratic regulator is really used. When I said before that a variant of linear quadratic regulator is actually widely used in practice, it's actually this one. It's called linear state feedback control. So let me explain that. I think we've seen it before earlier in the class, but I'll say what it is. It's a really simple way to control a linear system, or it's where people do it for nonlinear systems as well. It's just this. It's called linear state feedback control. Simply says, takes the state, multiplies it by a matrix K, and gives you, that's the input. Here, K is it's a single matrix. It's called the state feedback gain matrix for obvious reasons, right? Because it takes the states, that's xt, you multiply by K, and what you get are the inputs to apply. And this is very widely used, and it's especially used when it's vague about xt. The basic idea is that xt should go to 0 or be near 0, and t is not specified, right? So t would be specified typically in problems that involve things like docking or landing or something like that, where there's a specified time when you want to be where you have to be where you need to be. In many other applications, it's vaguer. It's like, no, I mean, follow this trajectory, or adjust my airplane so that I'm flying at, I want to fly at 40,000 feet level flight, Mach 0.82 or something like that. And that's and they don't say when, and you don't say 112 seconds from now. You just say no, just move towards that. And so that's the setting in which you would use something like a linear state feedback control, which, just for the record, is exactly how airplane control systems work. Okay. All right. So there is actually a way to choose k. It is the most widely used way to choose k. And now the derivation I'm going to show of it is not the one that you would normally see. What you would normally see is, well, it gets kind of complicated. There'd be things like algebraic Riccati equations, none of which you need to know, because I'm going to show you actually a simpler way that derives just from the constrained least squares problem that we just looked at. That's this. What we'll do is we'll set x desired equals 0. And then we observe that the ut is a linear function of x init. Let me explain why that is. Let's go back and take a look at that formula. It's right here. Y init x init appears in d tilde. It is in fact here you go. It's that entry right there. Okay. Now, when I go to a constrained least squares problem like this, the solution is actually linear in b tilde and d tilde. And you can check that. That comes directly from the specific formula for the solution that comes from the KKT system. Okay, so all right. So what that tells you over here is that in the linear quadratic, when we solve the linear quadratic control problem, what happens is that the first input, U1, is a matrix K times x init. X init is x1, by the way. We could find K easily. We simply use x init is equal to E1 up to En, and we solve the problem for each of these. We just calculate it, and that gives you K. So roughly speaking, what it says is that K is the thing that relates the initial state to the first action you would take when your job is to solve that linear quadratic regulator problem. Oh, and also, by the way, get in the end, after capital T steps, get to x desired equals 0. Okay, so that's the idea. Let's look at an example of how that works. So what we're going to do is the blue curve shows you what happens if you do this optimal thing and with a fixed deadline of capital T equals 100. Well, you do various things. This is the input you apply. You do this, you do all sorts of stuff, then you do something crazy at the end. I don't know what it is. But then it's all over at T equals 100, and then you're 0 here. Okay? Now, here's the state in that case, or the output. The output looks like this. It goes like this. It bumps down. And then at T equals 100 brings you to 100. That was actually the requirement. And then it's just flat 0. Okay? If you look at what happens when we take ut equals kxt with the matrix that is derived in that very simple way from that from the solution of the constrained least squares problem, that's this red curve like this. And it's asymptotically going down to 0. And here's the same one here, right? And so that's how that works. This is very widely used, right? So there are, in fact, packages that just will calculate these state feedback gain matrices for you. This is what they do. So